the topic today is about state machines. State machines is a concept that you have seen before, especially in the introductory courses for digital systems. And in digital systems, you mentioned or you talked about the two different classes of systems, which are the combinatorial digital systems and sequential digital systems. In combinatorial digital systems, the outputs depend only on the current value of inputs. So this means that the outputs are a combination of the input values. That defines a combinatorial system. On the other side, we have sequential digital systems, where the outputs depend on the current value of inputs, but also on the past value of inputs. And so we can say that the output reflects the sequence of input values, or in other words, the history of the inputs. In order to preserve the history, a sequential system requires memory. And that memory defines the state of the system. And so we can think about the state of the system as the information about the past history of inputs. What has happened in the past regarding the inputs that is relevant for what the system needs to do. And so sequential digital systems are also called and are based on state machines. And the formal representation for these systems, you all also know that, is by the concept of finite state machines. Finite state machines are representations of the system that rely on three concepts, which is the concept of state. In this case, I have forgot the name in the English. In Portuguese is tourniquet. I used to know the name in English, but I forgot. It can be in either two states, locked or unlocked. And by inserting a coin, I release this device. So I have two states, locked and unlocked, represented by the circles, and I have transitions from one state to another state, or sometimes from one state to the same state. And I have events which represent what occurs and causes the transitions. And this representation, we also have the definition of the initial state. So when the system starts, in this case, it starts in the locked state. Now, as we have seen before, we need state machines when we have sequential systems. So systems where the output depends on the history of the inputs. And as we are dealing with embedded systems often interact with the physical world. And so when thinking about our systems and when applying a state machine, we should have a vision like the one that's represented here. I have the embedded system. I have inputs to these embedded systems, which usually are associated with sensors. We get information from the physical world where the embedded system is. And then we have actuators, outputs that act on the physical world. And what we have to do is to look at this upper part, the embedded system, And our job will be to build the state machine that creates the desired relation from the inputs to the outputs. And so just a side note, this is an example of a simple cyber physical system. You will hear this word very often. And so a cyber physical system is any system that has this combination of a cyber component, in this case, our embedded system, and a physical world component. You have all reached some kind of solutions. There are many possible solutions for this, and this is only a possible solution. One thing that you have to take into consideration when you are designing this kind of systems is that the information that your embedded system or any system you are designing has comes from the inputs and nothing else. So every decision that your system takes must be based on some combination of the inputs, detecting that is 0 or 1, or it has achieved some, it has got to some value, etc. But only the inputs provide information for your system. So it means that you need to build all conditions based on the inputs to your system. So in this case, I consider for inputs, I have the remote push button. When I haven't stated the conditions here, so I can think that the system is closed. When I press the push button, it starts opening. And at this state, the motor is running in the direction is opening, and then it stops in the open state when the limit switch for opening triggers. So I have two limit switches, one for opening and another one for closing. Usually, we also have an infrared beam to detect problems. Sorry, and that means that we would need to have consider some other states, like when the infrared beam is detected when I'm closing the gate. Usually the gate stops and it resumes, usually opening again, but depends on the particular implementation. So what we have been talking about, just to summarize, are finite state machines. So these apply to systems that are describable by a finite set of states. This set of inputs or events can trigger transitions between these states, and the behavior of your system at any point in time depends on the state and inputs. Again, the example of for instance, the infrared beam. When we are opening the gate, usually the infrared beam has no effect. When we are closing the gate, the infrared beam stops the gate from closing. And so for each state, the system may be, the behavior is defined for each possible input or relevant input or event. It doesn't have to be for all possible inputs. And the system has some particular initial state. The representation of these state machines, it can be either by these the diagrams that we have seen, or we can use what's called the state transition table. This is a table where I have the current state. I have one line that corresponds to each current state. I have one column for each possible event. And then here I have the next state based on the current state and the event that has occurred. In this case, when I'm in state locked and I insert the coin, the system goes unlocked. If I have current state locked and I push the gate will remain locked. So these are two equivalent representations of the same system, and I can use also something like a ball type to represent the initial state. The readings that you were proposed were about UML state transition diagrams. These are the representation of state machines in the unified modeling language. And they rely on these 5 concepts. First, the one we have seen, the state. Each state must have a unique name. Then you have activities, which are the computations that occur inside the state, but do not cause state changes. Then I have the events. It's what causes the state change. And then here in the UML transition diagrams, I have 2 other things that do not occur in other representations of state machines. Is that I have associated to the event, I have a guard, which is a logical condition that must be true for the action, the transition to occur. And then I have an action, which is something that happens during the transition. So you can see this is a more complex and richer representation than the simple state and transition diagrams that we have seen before, and it can represent more complex systems.